All right, are you guys seeing the slides?
Looks good.
All right, perfect. All right, so thank you guys for joining us. I wanted to present today about an instrument concept we're developing for Magellan called Mirmos, the Magellan Infrared Multi-Object Spectrograph, which is an instrument concept. We're still searching for funding for this instrument. It's PI'd by Nick Conadaris from Carnegie Observatories, and I'm one of two project scientists along with Drew Newman. Some of the key instrument team members who have been doing a lot of work on this project are Jason Williams, who's a graduate student doing his dissertation at Carnegie, Alicia Lands, who is a postdoctoral fellow at Carnegie, and Tyson Hare is our lead engineer. And I also wanted to highlight the CGM science team, which includes Sean Johnson, who I believe is on the call, Xiaowen Chen, who's been participating in the KIT workshop, as well as myself. And we are more than happy to hear about other ideas for use cases for this instrument. As I mentioned, we're proposing for funding. And so if people have killer app ideas for this, I'd be delighted to hear about them. All right, so what is Mirmos? So Mirmos is a multi-object and integral field unit that's operating in the near infrared at a resolution of about 3700. It's really optimized for faint object spectroscopy of galaxies, as well as studying diffuse emission from the circumgalactic medium. It has a second mode, which is aimed at high spectrophotometric precision observations of extrasolar planet atmospheres. So a very different use case. And as I mentioned, it's slated for the Magellan telescope. So how does this work? What's the basic principles behind the instrument design? So here I'm just showing a cross-section engineering drawing. And what you can see is there's a set of 5 cameras down here at the end, which is fed by a dichroic tree structure, which has often been used in the optical, but less commonly in the near infrared. And what that means is that we can simultaneously observe in spectroscopic mode Y, J, H, and K. So we get the full near infrared passband in a single shot, in addition to a small camera that's an I-band imager, which is used for the exoplanet science case, as well as for aligning the slit masks. This is at sort of a moderate resolution of about 3700. It's optimized for each band. And there's 2 different front-end modes. So one of them is a multi-object mode, which covers a pretty wide field of view, 13 minutes by 3 minutes, with about 100 slits with a cryogenic configurable slit unit. And then that whole slit unit can shift out of the way, and an IFU can come into the focal plane, a slicer-based IFU. Which has actually an enormous field of view, at least for the infrared, 26 arc seconds by 20 arc seconds, which I think is really outstanding for CGM science cases. So this gives you some perspective of the landscape of what exists for studying diffuse emission and other topics using wide field near infrared spectroscopy. And really what this shows is that the focus of the community has actually been on very good angular and spatial resolution with AO-fed instruments largely, as well as the planned JWST near spec that should fly next year. But what this means is there's been a lot left on the table in terms of wide area coverage in the infrared. And so I think that this is a really important way that Mirmos is going to contribute a huge amount, especially to CGM science. Okay, so just jumping into the science use case for the circumgalactic medium. Here I'm showing 2 sets of recent data on CGM science cases from Xiaowen Chen and Sean Johnson. And the idea here is basically that they have used, in this case, MUSE, to detect H-alpha and nebular oxygen-3 emissions, so rest frame optical lines around a group of galaxies, as well as around a quasar. However, using MUSE or something like this, we're limited for these lines to redshifts less than 1. And so the idea is that with Mirmos, we can detect, resolve, and map the circumgalactic medium in rest optical lines at redshifts greater than 1 for really the first time. And the reason why that's so important is that these rest optical lines are optically thin, and so they're really great kinematic tracers. In addition to that, if you combine the information you get from these sort of typical like nebular diagnostic lines, you can learn things about the ionization mechanism, constrained masses of gas in the CGM, et cetera. So I think this is just really, really exciting and could open an interesting window for doing sort of this morphokinematic mapping of greater than redshift 1 circumgalactic medium. So this is really what I consider to be sort of the killer use case for CGM science. But since I have you all here, I also wanted to mention that in addition to this, it has a bunch of other really cool science cases that I think may be of interest to people on the call. So I've highlighted on the top here the main sort of CGM science case. But in addition to this, the wide field of view and multi-object mode can map the topology of late reionization using basically redshift greater than 6.5 galaxies, not just detecting Lyman alpha emission or absorption, but also detecting metal line emission from these galaxies. We can also map the large scale structure of galaxies around cosmic noon and really try and connect how galaxies evolve based off of their position within the cosmic web and the large scale structure of the universe. The IFU will also be really helpful for characterizing sources discovered in next generation wide field surveys. And the exoplanet science case is really focused on understanding the molecular content of extrasolar planet atmospheres. So that's sort of the wide science case for Mirmos. And if anyone has a question, I'm happy to take it. Cameron.
Will you be able to do traditional UV rest frame UV transition stuff for higher redshift with this? I mean, you talk about using Lyman alpha at high redshift, like above 6.5, but do we expect that there will be bright enough background sources to be able to do traditional absorption line studies of the CGM at those very high redshifts?
So I think the challenge there is really just having sources that are bright enough, and whether this is really the type of spectrograph you'd want. So I think for certain sets of absorption lines, if you have a bright background galaxy, you could plausibly detect them, but they'd have to be very bright. I think most likely it would still be quasars. For Magellan, we have FIRE, which Rob is on the line. He built FIRE for this purpose, and it's amazing at observing high redshift quasars. So so depending on exactly what use case you're interested in, there is the plausibility there. But for this this very high redshift reionization case, we're really talking about looking at Lyman alpha in emission and other emission lines, which have been shown to be very, very bright, have extremely high equivalent widths at redshift greater than 6, things like carbon-3, carbon-4, oxygen-3, et cetera, these sort of semi-Ferdinand lines. Okay.
Hey, Gwen, I'm not sure if you can see the chat right now.
I cannot.
Okay, yeah, so we have a few questions. One, will it be doing nod and shuffle for the IFU?
There is no current plan to do nod and shuffle, no. It uses the full detector to get that very large field of view.
Great, okay. And do you worry about cosmological dimming for your intermediate to high redshift sources?
Cosmological dimming. So are we talking about the 1 + e to the 4th issue? So these observations that I've been showing have, when we do exposure times, we calculate them using surface brightness dimming, basically the expected values. And we still think we can detect these if we had the exact same luminosities, line luminosities, we would be able to detect them in modest integration times, depending on the redshift, between like an hour and 10 hours, depending on the redshift and the exact use case. But we believe that these things are detectable at sort of these moderate up to cosmic noon redshifts. So.
Great.